the storm is here, and from this point, of course, the performance of a plant decreased. And most of the time, things are somehow balancing, because if you have, for instance, the rain is coming in April, maybe May will be dry. Straight flow of the beginning exploded into now different possible behaviors, clusters.
Hello, welcome. It's nice to meet you all. Good morning, good afternoon, good evening. We are around 200 people registered for this webinar, coming from around the world, so from Europe, from Asia, from North America, South America, and also Africa. So do not hesitate to say hello in your own language in the chat box. It's always a pleasure to get to know you guys. I want to welcome you all to this new Sinovoltaics webinar. As you can see on the screen, I am Arthur, and we're going to explore an exciting new topic today, which is to discuss PV plant optimization techniques. So if this is your first time attending a webinar by Sinovoltaics, please know that our speakers will dive for around 30 minutes into this topic, and after we'll have a 15-minute Q&A. So you can ask questions using the chat on the Demio platform, and after we can discuss those. So today we have the chance to host Xavier Daval, the CEO of Kilowatt Sol. Xavier has been active for more than 20 years in the solar industry. He is a vice chair of the Global Solar Council. He is also advising the French government on several matters. Before that, we'll have Niklas Weimar, which is the CTO of Sinovoltaics, and he has a really strong experience as well in the solar industry for more than 15 years, especially in the quality control of factories in Asia. And if I may say, last but not least, myself, Arthur, also active in the more specialized into energy storage for more than 5 years, and I am the head of technology of Sinovoltaics. In today's session, I will basically moderate the whole session, so if you have insights, feedback, and also questions, do not hesitate to share those into the chat. Before we jump quickly into the webinar sessions, a few words about Sinovoltaics. We are what we call some technical compliance firm, meaning that we specialize into reducing the supply chain risk for large solar and large energy storage projects. And those supply chain risks can be basically defined into two categories. First one being quality, where we are best known to perform factory audits as well as pre-shipment inspections. And also on the other side, traceability and ESG, where we will map basically the suppliers of your own supplier and check the performance of those. So we're going to focus on PV projects today, but have in mind that we perform factory audits and pre-shipment inspection on a wide range of components. Basically, every component of a utility scale solar project, modules, transformers, inverters, mounts, floaters, and also energy storage system. All right, so now I leave the floor to Niklas. Niklas, floor is yours.
Yeah, thank you. Thank you, Arthur, for your introduction. And also from my side, welcome to this webinar. It's a pleasure to have you all here today. So today in today's webinar, we addressed I would say indeed critical topic, which is PV plant optimization techniques. PV plant optimization already starts as early as when decisions on the components of your PV plant and the suppliers are being made. So we will look at a solid approach to PV plant optimization involving critical aspects and items to consider in order to mitigate the risk of an underperforming deficient PV plant. They involve standards implementation, origin tracking, large-scale quality analysis, inspection and supervision at the factory, and diagnostics involving the existing PV plant. So let's have a look at each of these. The critical foundation of a well-performing PV power plant, we'd say, begins with clarity about and agreeing with the factory on the quality level of your components, such as the PV modules. Designing and implementation of a reasonable quality standard as part of the procurement a contractualization process. So when you sign a contract, is a critical factor to decide on the workmanship and performance level of your components later on in the plant, and provides therefore a degree of quality planning safety. There can be multiple approaches to this. So one way, for example, is to review the factory internal quality standard and adjust it when necessary, especially in view of the component technology board and the project's requirements. Another and more preferred technique among many project developers nowadays is having a more strict standard, which is separate from the factory standard, and which can be either the company's own quality standard or one provided from technical consultants, such as Sinovoltaics. Another solid pillar of PV plant optimization is to know where your equipment comes from. So this is these days not only important from a supply chain mapping point of view, so to meet regulatory requirements, but also much more to mitigate PV plant performance risk in the long run. So many known and large brands, be it makers of PV modules, inverters, transformers, and so on, they recourse to OEM manufacturing at manufacturers that most project stakeholders may probably have never heard of. And have of course no clue if the OEM maker is able to manufacture the product on the level its subcontracting brand client can actually achieve. That being said, so quality supervision of those OEM makers by the brand is in some cases also rather poor or lax, and especially more so when the OEM maker is located in another jurisdiction and stuff that needs to be dispatched overseas to that jurisdiction for monitoring. So important is here to specify already clearly the factory location of your components in your contract and perform a proper audit of the factory concerned, so that factory that is going to make your equipment. Let's look at the next pillar, which is large-scale quality analysis, or you may also say mass testing. So the standard in the industry is still to use basically sampling with internationally widely adopted sampling standards, such as from the ISO. And on the basis of this standard, statistical conclusions about the quality of an inspected batch can be drawn. This is certainly in many cases a practical approach, given often the huge quantities of single products that can form a single batch of a shipment, and especially then when coupled with proper and continuous monitoring of production, so to minimize the risk of time intense and costly deviations. But exemplifying the case for PV modules, given their critical role in a PV plant and the lion's share in overall equipment cost and the highly competitive corner cutting happening with PV modules and technical compliance issues often involving this component. So, so large-scale quality analysis is again, solid foundation of an optimally performing PV power plant. Such quality analysis can be performed with Sinovoltaics AI-based EL mass analysis software solution, or we call it short SELMA, which can detect and classify up to 15 different defect types at over 99% accuracy and very high speed. The defects, or such defects identified, or that can be identified, involve various types of micro cracks, grid finger defects, cell breakages, disconnected cells, and solder faults. Issues, if not removed in the initial stage of the module's life cycle, will show up in the later stage and unleash their costly impacts on the whole project. And this is a subject also that my dear colleague Xavier will address today in more detail. Unlike a bit of sampling here and there, so such large-scale on-the-fly analysis enables project developers to filter and thus replace the rotten or all rotten apples from the shipment basket before they reach a PV plant and basically cause trouble in the long run. Another pillar carrying a solid PV plant optimization roof over its head is the actual inspection and supervision on site at the factory. So this is not only to ensure that the standard is as agreed in the initial solid pillar, so that it is implemented, as per contract, or it's not only to basically ascertain that the product is actually made at the factory, which was agreed on in the contract, or hopefully agreed on in the contract, and then also audited before, but it also serves to basically ensure that the manufacturing processes are in line with best practices, and the quality management systems are actively up and running at that factory. Furthermore, inspection and supervision enables quick troubleshooting of issues and support in the replacement of rotten apples caught during large-scale quality analysis, so that a 100% quality compliant batch of components can reach the PV plant. And now, having spoke about SOLI, so coming to the critical pillar of Diagnostics D, I would like to pass the word to Xavier from KilowattSol. Xavier, the microphone is all yours.
Thank you very much, Nick. It's a pleasure to extend. I think we are working on the other side, but exactly on the same topic, trying to improve the quality of the project. If I succeed, I will share my presentation. I hope you can see my screen. Yes, it should be there.
Yeah.
So good morning, afternoon, good evening, according to where you are. I'm actually very happy to present to you today. Today, shall I see? In a nutshell, we'll introduce that I'm the CEO of KilowattSol. KilowattSol is a technical advisory, but we are probably more than that. We are a group of technical experts, very passionate with the technologies, physics and math, and we try to invent the tools that we believe this new industry is needing. Myself, in a nutshell, my background, I'm a electronic engineer, but I've done plenty of different things in my life. And today, and for the last 15 years, I've been working in this industry. I'm, as I say, vice chair of the Global Solar Council. I'm also vice president of the French Solar Association, and I'm chair of the Solar Commission. And I have plenty of other functions, so I'm a very busy guy. And today, I think we had a discussion preparing this conference with the Sinovoltaic teams, and already what struck me was definitely that a picture worth 1,000 words. How to see what nobody's seeing when we talk about a PV plant. And actually, I'm sure you guys listening to me, if you are operating a PV plant, the big challenge is to detect when something is going wrong. And most of the time, the tiny problems that the plant might have here, there, whatever, takes quite a long time to pass the threshold of sensitivity and become obvious that something is wrong. On the story I'm going to share with you today, definitely is working about the same. We talk about here, it's a client of ours with a 5 megawatt plant, PV plant. I mean, 5 megawatt peak. It's reasonable size PV plant, equipped with horizontal trackers, 5 inverters, 800 strings, 19,000 modules. So it's a significant plant, but it's not that big. It's just the typical plant. And the story really started when in March 2017 in France we had a storm named Zeus that hit France with a very high speed wind, 130 kilometers. So I don't know what it is in other units, but it's serious wind. And unfortunately, the PV plant was hit by the storm with a lot of defaults. And this was the starting point of the story, because from this day, the plant, so you can see that I need to show my, sorry. So the storm is here, and from this point, of course, the performance of a plant decreased. But the storm arrived quite at very early stage of the plant. The plant was 3 months old. So, so for the clients, the client enters in this period of problem, recovery, and after a certain time, never really reached the performance he was expecting. And that's because of the storm, it focused on finding what's wrong. And in the mind of the client, the wrongdoing was the consequence of the storm. And that was what triggered the investigations, including the involvement of Kilowattsol. Just for the record, the first thing we did as a technical advisor was to get a sort of a value of what the plant should be doing. That's a yield study, a greenfield yield study, yield estimate we did. On the yellow line is the one of Kilowattsol. And the green one was the one performed by the technical advisor prior the building of the plant. So I don't know who's right, who's wrong, because it's always, you can challenge the database of climate, you can challenge hypotheses in your PV system, whatever you want to do. But at the end of the day, reality is probably in the middle. So what we try to do at Kilowattsol when we are facing this sort of investigation, the plant is not working well. What's the problem? What's the root causes? The third thing we look at is the climate, because unfortunately or fortunately, years are not equals. You've got good years, bad years, good month, bad month. And most of the time, things are somehow balancing, because if you have, for instance, the rain is coming in April, maybe May will be dry. Hence, overall, 1 year, if the rain is in April or in May, it's a bad May and a good April, or vice versa. And this is exactly the swing you are seeing. The red line is what we call the climate anomaly. It means what is the distance of this very month here against the typical long-term month. So a bad month here, very good, extremely good one, and so on and so forth. So if you have your monthly production, and if you know the anomaly, you can try to balance it. And this is the exercise we are doing here. And if we consider a 12-month rolling sum, so each bar here is a 12-month value, if it's neutralized of the anomaly, it turns into the red line. And you can see that the red line, once normalized of the anomaly, should and is rather a straight line, except the repairing period of the project. But once after, you've got quite a straight line. And the third thing that struck us when we started this analysis was the gap between our hypothesis, is it the one of Kilowattsol or the one of the other advisor? It's not very important, but a significant gap between the stabilized performance and the expectations. So something was wrong. What was it? Unfortunately, at meter level, it's not sharp enough to see through. So we had we had to dig further. So we decided to dive at string level at our resolution. So here, this is the plot of the 850 string of the plant on a hourly basis. So it's a starting point on what your eyes, I talk about this, this picture that's worth 1,000 words. Your eyes, like mine, can immediately see a series of things if we look at it. So the third thing we can see is that obviously not all the strings are following the same path. It means there is different behaviors within the plant. And another thing that struck us was somehow the thickness of the plot, because in a PV plant is something very basic. You've got a series of modules linked together. That's a string. Then you've got 1, 2, 3, whatever number of strings per input of your inverter. And after you've got 1, 2, 3, whatever the number of inverters. But if you are on a plain field, which is most of the time the case in the solar industry, if you are in your plain field, if all the modules, tracker or no tracker, are receiving the same amount of light from the sun, they should all behave the same. So they should be in a sort of narrow, sharp drawing. Here, definitely this 10% of spread was a question. So at KilowattSol, we have engineered tools to read the data, because of course the client has the data, the OEM operator has the data, they have a lot of data, but what do you do with them? And handling a huge amount of data start to become a challenge if one doesn't have a dedicated set of tools to see through, to play with them, to make them visual. So that's here that we introduced a clustering methodology. And the clustering methodology actually is doing what your eyes would be doing. With your eyes, you see the one that are alike and the one which are different. The thing we ask the system to do is definitely to let the machine cluster the packs, what is alike one color, what is another behavior, another color, and so on. And we let the machine who operates with back and forth input from human beings, because, for instance, naming, labeling the string is something that only a human being can do. I can say, okay, I want to name this one as working fine, this one as working wrong, for instance. The machine doesn't care. For the machine, this is digital, this is cluster 1, cluster 2, cluster 3, whatever. Okay? And also, the sensitivity of the clustering is also a parameter. If I put the matter meter at the maximum sensitivity, if I have 850 strings, the machine can detect that the 850s are different. But this is not what we want. We want something that works alike. So we have to adjust the sensitivity to cluster in something that really means from our point of view, and that's enough. So this is what we have done. So imagine we are on a given day, we upload the 850 strings of the plant, and we let the clustering work. And the first output we have here is that the computer decided to split into 3 clusters, cluster 0, 1, and 2. Cluster 0 is blue, cluster 1 is red, cluster 2 is green. And obviously, you would do the same. You would say the red one is not working. The green one, sorry, are not working. And what you can see, so maybe I will explain a little the physics. We talk here about a horizontal tracker. So horizontal tracker is following the sun, and until noon, and at noon is flat. And because it's flat, it's less performing than when it's more facing the sun. This is why you've got a sort of M shape, where the bottom is noon for the light, not noon at the clock, but noon for the light, and a little higher shoulders in the morning and in the afternoon. And what we can see is the red ones are not moving. So they behave like a fixed tilt PV plant with a sort of triangle or A shape or bell curve, whatever. Okay, so obviously the three clusters, we can have clusters with moving tracker, that's the blue one. We can have clusters with a fixed system somehow, that's the red one, and non-responding strings, that's the green cluster. So we can name them, but manually we'll input that we will call that the nominal or normal ones are the blues, subnominal is not performing, and the faulty ones are the red. And what is interesting now is to look at how the clustering software, the machine learning software, is keeping track of what we have been taught it. Hence, is it keeping the naming throughout the time, not mixing the clusters, and it's working well. We see that we were August 11, we are August 15, and it's still coherent with the same colors or whatever. Now we move to another. Sorry for the math today. I don't want it to make it boring, but here the thing is, what your eyes are perfectly seeing, the fact that the blue curves and the red curves are different. It's complicated if you want to do that throughout a long period, because we are looking at a daily basis over a series of months. And it could, and for a large number of strings, 850 is here. So it could be complicated. So what we decided to do is what is called principal component analysis. It means that we were gonna reduce the number of dimensions. The typical day is 24 hours. I have 24 values. 24 values is a lot. So if I do this dimension reduction, I will try to display the same thing, but into a two-dimension referential. So here I've got one axis, another axis. And on this one, if the math is correct, I will have my cluster very differentiated, separated. This is what I want to achieve. And I've got my reds, dots. One dot is one of the line here. The blues, one dot is including this one, which are a little separate. Probably they are the one which are on the side of the pack. Okay, and the greens are here. So this is the first transposition. So now for every day of my analysis, I've got a two-dimensional plotting of the strings. So it means that now the plots, I can present them as a chronicle series of dots. So imagine that each of the line there are strings, and this is the time from starting point till the end of the analysis. So it's likely like Tour de France. At the very beginning, I've got my pack of cycles, you know, my pack of strings, and they are very, very, very packed together. So they behave the same on this kind of a straight line. Everybody is following the same path, following the same behavior somehow, and that's okay. And at some point, I may have once in a while a couple of strings that are faulty, you know, a fuse or I don't know what it is, and so they behave separately until puff, back in the track. They've been repaired. And we'll see that these kind of things will happen here and there over the life of the plant. This is the normal behavior of the little failures that any power plant can have. The big things was here that the storm here really behaved like an explosion. You've got all the cyclists, you know, on the ground. It's a big mess. And everybody has to come back on the bicycle to start again. So you see that this period here is complicated until some of the systems will go back into a form of normal behavior. That would be here. Some other, because they are blocked, looking east, looking west, looking horizontal, twisted, whatever. And so now the straight flow of the beginning exploded into now different possible behaviors, clusters. And this is with that very visual until, I would say, somehow everybody is back on track. Maybe to give you a better flavor of this, I will share another format. I don't know if you can see it. So this is the thing. So as I was mentioning, I can select any of the string of the PV plant. So initial phase, the 4, 5, 6 strings that were faulty. And because they are faulty, they all behave the same. Because, for instance, 0 is 0 for everybody. That's rather fast. And you see a boof, you see that the faulty one, back on the pack at this very time. So that's it. And after we see that according to the direction we looked, we have the storm, and we have this explosion of behaviors where a sort of a tornado thing, and it's very visual here, everybody direction. And after a while, you've got some following east, some following west, back on track, more or less. Maybe there is some period where people were coming for the maintenance, fixing thing, disconnecting the plant, reconnecting the plant. So it's this phase is a work in progress phase, and some of the strings are following this route, and you see there is other routes, and on some these strings up there never been reconnected, and they still life ahead. You know, but at the end, you find more or less a uniform pack like existed at the very beginning. So this is a nice object. I'm back to back to the presentation. Sorry, up. So once we have this tool, we can see what is working visually or mathematically. It's the same. Means that we can split in different buckets, and now diagnose a little further to try to understand why something wrong. And this why working wrong, because on this story, this is a bad story, but we could do the same exercise to improve, of course, a performance of an existing plant. So what we realized was the spread of behavior, as I said, from the beginning, the thickness of the curve is the question. Because if we only focus on the working strings, then there is no other default. These are the ones working. If they are working, why it is spread? And investigating this thickness, the only answer was that the wattage of modules was not coherent and consistent with the nameplate value. It means that these PV plants, even before the storm, never really received the accurate wattage of modules. The labels were fine, but only the label, not the performance. So that's a big challenge. Unfortunately for the clients, the manufacturer of the module is no longer there. So it was impossible to go back and to prove the points. So that's a big issue. But definitely, there is no other explanation but the fact that physically, some modules never had the wattage that was flagged or labeled on the back of the module. Second thing was the tracking algorithm. And if we consider the theoretical tracking with wider shoulders from the system, if you have a too safe backtrack, you start to go back into following the sun too early, and this is the amount of energy lost according to the period of the year. And that also could be measured and could be demonstrated at any string level. This story, as I said, when we were involved, was already in court. And so I don't know if you guys are familiar with this kind of context, but when you step in these kind of things, you have the experts of the EPC, of the OEM, of the tracker manufacturer, of the module supplier, or whatever. I mean, you can have 1, 2, 3, 4, 5, 6, 7 experts around the table, and it's always a nightmare. Kilowatt-Sol, we were advising the owner of the plant, and we came on board with fact in order to help the judge, the court, to frame the troubles. So with the accurate tool we've been providing, it was able for us to split in different buckets what is what. What is the amount in euro of any of the penalties? And at the end of the day, you see that the storm itself, I mean, means the stop of operation was very short. The day of the storm was 2.24%. But after, we also measured that the downtime of the plant, what we call downtime, the typical downtime of the plant, was just amounting to 1% year on year, because you've got for over 3 years. You can see it's not much. The typical, what should be named plant downtime was okay. On the year of the storm, the tracker downtime was probably above average, with 1.6%. But at the end of the day, the typical off track of the trackers for maintenance, for whatever small blockage, is not much. But now, if we consider the two other problems we flagged, means the module wattage, unfortunately, amounting to more than 7%, you cannot recover, especially when the supplier is no longer there. On that, it lasts for the life of the plant, and it's permanent. So it's not a degradation or whatever, because if so, the amount should be moving. But definitely, we talk more about an offset of value that the plant received, and that's forever. On the other side, I would say the off-track, the fact that the tracking algorithm is too conservative somehow, that can be improved, and it has been improved in between. So it was not a full recovery of the 7%, but a partial recovery of this amount. So now to wrap up I hope it was not too much. I just tried to list a few things I want to share with you guys as a takeaway. First thing, be careful. A PVsyst report, Greenfield PVsyst, is never a proof. It's of course, the more accurate it is, the better it is, but it's never a proof. But it's sometime, if it's sharp enough, a reference figure that helps you to see if things are going well or going bad. So it rings a bell somewhere. You have to have that, but it's never enough. Unfortunately, from my experience, in standard conditions, it takes years to realize that something is going wrong, because most of the time, the default we are facing in our analysis can be very small. We talk about 0.5%, 1%. And in my opinion, something below 5%, nobody can see, because we are not prepared to sense something below 5%. And when it's above 5%, it's a big thing. But even though maybe it takes 1 year, 2 years, because last year was not complete, we started the work in the middle of the year. Then the year after, we had this, I don't know, big event or storm or whatever that is blurring the data. So most of the time, it takes a while to sense something is going wrong. Definitely, one thing I recommend is, if you have a question and if you want to measure if something is going wrong, you need your initial reference, what I call T0. And the T0 is something that has to be taken into account at the very beginning. You have to record the proof of what you received somewhere. Hence, if I have something later down the road of the life of the plant, I can measure Tn minus T0, because I know the two performance, and I have proof, and I have to have, I would say, binding proof. So something that I could use in court in case of. So that's very much a takeaway from me. You have to have your T0 reference somewhere. And last but not least, this is, I hope, what I have tried to demonstrate with this presentation. If you have an objective demonstration of what is what, you can win the case. Because unfortunately for us, I imagine that a lot of people listening to this webinar are from a technical background. The thing is, we engineers, we understand. But unfortunately, once you enter, I would say, the court's route, you talk to people which are lawyers, and they have no technical clue. They don't understand. So if your proofs are not very visual, easy to understand, there's always going to have another expert telling something opposite, whatever, and they're lost. So having something sharp, but also visually strong, is a must-have to prove your case. I've done, I imagine there is some question, and I will be very happy to answer them. Thank you very much for your attention.
All right, thanks a lot, Xavier. That was super interesting. I really like the whole like Tour de France storytelling. I think it was great. All right, so I see we start already to have questions pouring in. Do not hesitate to add yours. All right, I will select this one first. From Fajri, as online IV curve testing is available more and more from the inverter manufacturer, for the Persian Grow and Huawei, is it possible to replace offline IV curve testing completely? Do you want to take care of it, Niklas or Xavier?
Yeah, definitely. So we work very closely at KilowattSol. We do a lot of R&D, and we do joint R&D with Huawei, for instance, and we've been working on this very topic, because the IV curves, the automated IV curve is something very smart. So definitely, and I imagine the SunGrow version works the same. I'm quite convinced in the future is going to replace the physical test, because we know that the physical test requires certain sky conditions to be performed and so on. So they are very well. And once again, we are entering, I would say, an era of data. And what such technologies are providing is that you've got IV curve for 100% of your string at the same time. Hence, you no longer need a pyranometer to catch the sky, because you don't care, because the sky description, you've got it embedded in the number of tests of measurement you've performed. So that's the reverse. So you disconnect from the requirement of a proper measurement of the entering light. So, which is why at the end, such a methodology works better than a poor on-site IV curve measurement. The thing is, and that's what we've been doing with Huawei, for instance, is when you have thousands and thousands of IV curve, and this is where clustering, because we do exactly the same exercise we've been showing here, but we've been doing exactly the same with Huawei at PV plant with which are 100 megawatt, 200 megawatts. So you can imagine you have quite a few IV curves, and we use same clustering to sort them. Because what we want is to spot the right ones, the good ones, and also to be able to do what is easy to do when you've got 6 or 7 IV curves to look at. But when you've got 1,000 on 1,000, you have to have automated software to handle the volume.
Okay. Maybe some follow-up questions regarding IV curve for you more, Niklas. Is it common to see PV modules that are underperforming for when you do flash test at the factories? Because from the case of Xavier, it seems that those modules were already underperforming before the storm. So yeah, so do you see is it common for you to see underperformance for IV curve at the factories?
So Xavier touched upon a very important topic here, which is actually, you need to know T0, right? And it's all about basically then at the factory level to have the already basically before it leaves the factory at that level. So to have actually, a precise actually calibration of the equipment as much as possible, of course, in that mass production environment, to basically get as accurate data as possible. And then so to start out well. So that's just basically to get back on that point from Xavier. Now what? Oh.
Yeah, Nick, once again, sorry to emphasize the point. It's very important. You have to have accurate and opposable. It means that it has to be obvious, because the day you enter a sort of conflict, any piece of proof you put on the table has to be sound. So if it's just, a factory, whatever, you don't know if the machine was calibrated, right, whatever, it could be weak. So you definitely have to have something that can stand in front of a court. Unfortunately, you have to think about that at day one.
It's you basically need really for the non-technicians basically need like the proper and sound evidence, and that basically needs to that needs to be as Xavier said, plausible, and it needs to be also demonstrated. So you cannot just easily pull out some Excel sheet, which is then probably would have probably issues in the examples that also Xavier mentioned. So what we see in the factory level, if properly calibrated, then it's mostly fine nowadays. It used to be worse before. It is rather than issue, especially with the, let's say, from experience with the less known or experienced factories, and then we go back basically to the point of like OEM or so. So often the modules that you see like with these very nice big brands, they do not necessarily come from these same floors, so to say, and then there's less experience with a less well set up factory starting out measuring these modules, and then you get sometimes in some cases we see actually a surprise at the when cross-referencing with laboratory equipment. Yeah, this is actually ideal case if you can have some cross-checking also with the laboratory, because at the factory floor you get only to a certain measurement tolerance range, and which can be a little bit more improved at the laboratory level. So to get more to the precise T0 that Xavier mentioned, the more precise the better. Yeah. So that was the lengthy answer to that.
All right, thanks a lot. We have a lot of questions. I have to pick some actually. But maybe we have this a clarification question for Xavier again from Eduardo. Congratulations for the presentation. Can you explain the plateau of the M shape at the noontime? Is it performing less because of the higher temperature?
So no, it's not temperature exactly. It could be, but it's not the main point. It's definitely physics. Sorry, I'm trying to use a visual. So if my modules are flat, the sun is here, going up, going down. The projection of the sun is the A shape, is the triangle or A shape, you know. Now, if my modules are on a tracker, the sun is here. The sun is here. And now, when the sun is moving, it's gonna go up. But because here the PV plant is in the northern hemisphere in France, the sun is actually lower in the sky. It means that when I'm flat, in the morning I'm better, but at noontime, the sun is more horizontal. So the angle is not perfect, which is why you've got a drop in the collection of the stream of light from the sun at noon. And after, in the afternoon, it returns into better. This is just a geometrical effect. If you are, if you are closer to the tropic or equator, you don't have such an effect. This effect is very much a European effect, or a northern or southern hemisphere, where at the end of the day, at noon, this is somehow the worst condition to collect the sun because you're flat.
All right, thanks, Xavier. Another question, maybe if you have some time left, from Mary Joyce. Thank you for the presentation. Thank you for the presentation. If I may ask, in your evaluation, do you account for the irradiation values as well as from the generation production of the streams? Yes, that's for you, Xavier, again.
No. And this is once again, irradiation reference is conditional to the quality of your setup, of your sensor, of whatever. And the good thing with the clustering is once you have access to 100% of the plant, you have all the information you need. And what we do on the quantification we provided to the court at the end is based on what? We look at all the strengths. We keep the 85% segments of the top performing, you know, not the top one, but in the reference we take is the 85 quantum, the most performing 85 value. And we say, okay, that's a reasonable representation of what the plant can do. And I don't care about the irradiance. I just say, from the track record, from throughout the life of the plant, the percentile 85 is somehow presenting what the plant can do. And everything below is lesser performing, that is 85 reference. And I'm not talking about the top one, the 100, but the 85.
Thanks, Xavier. Okay, maybe another question from Tayab. How do you differentiate between the string outage and shading in winters?
So, sorry, for the purpose of what we had to do, that was not the point. We don't care. If everybody's shade, everybody has the same notch in the curve. If everybody is alike, that's it. So we demonstrated on a separate exercise that the tracking algorithm was not optimum, that it was too conservative. And we had the exchange with the manufacturer and we agreed on the fix it. So that's one thing. So we don't talk about that. But the fact that there is shade, if everybody is shaded at the same time, or if, for instance, at some strings are impacted by a shade, not the other one, like the border one that could be near a tree or whatever, okay. That's just a question of sensitivity. And have you seen in the different visual, sometimes you've got some blue lines which are not exactly following the pact. It's not important because we can have a side effect on a few strings which can be considered as normal, working well, even though they might have specifically here and there a different behavior. So it's not a major problem. For the sake of the analysis we're trying to do, what we try to do is to say, okay, now that we have identified the working pack, the one that works, that is sound, we take from the working pack the percentile 85, the one which are at the very top, and that is giving us the reference performance of what should be the ideal plant when everything is working well. And after, if everybody is in a very shallow bandwidth, that's fine. But once some are too far away from this, it's not normal. And definitely, none of us are expecting our plants to behave in a large spread of response, because this is against the nature of a PV plant. A PV plant is like Lego bricks. You've got 1 brick, 2 bricks, 4 bricks, whatever, and they should be all square and white and whatever. It should be the same.
Great. So actually, we're already over time, but maybe if we have time for one last question from Shubham. Thank you for the presentation. How do you decide on a nominal cluster from many suboptimal clusters?
So most of the time, I mean, I don't know what is the exact question behind Shubham. I'm sorry for that, but how I interpret it is we use typical parameters to run through, and as I say, according to the sensitivity we put in the software, we could have 850 clusters. This is not what we want. So we try to do something smooth enough to make big bulks of families. Like I was presenting early, I want my red, my blues, my green, and that's enough. Because of course, if I put the sensitivity higher, I would have made, instead of 3 buckets, I would have 4, for instance. The morning one, the afternoon one, the flat one, 5, what I'm saying 4 maybe. So the 0, I would have the 0. I would have the M shape. I will have the A shape, or maybe I will have also the A shape looking in the morning and the A shape looking at the afternoon. And I would have 3, 4, 5 clusters, for instance. But this is not what I want. Here, I wanted to focus on the working one, the medium one, and the 0 one. So that's where we adjusted. And maybe at the first try of the software, maybe we had 5, 6 clusters. We say it's too many, and this is just an adjustment. Because the point, I mean, the tool is used to demonstrate something. Here we wanted to quantify what is working more or less correctly, on what is average, and what is not working. So that's why we decided on this adjustment.
All right, so we still have some questions not yet answered, but I'm sorry to say that we're quite running out of time, and we are at the end of our session of our webinar. So actually, what I would suggest you here, if you still have questions, do not hesitate to contact Xavier, obviously, also Niklas and I, if you have questions more related to Sinovoltaics. And I think anyway, it was a great pleasure to have you all here today, and we had great presentations from Niklas and from Xavier. So thanks a lot, Xavier, for your time. And
my pleasure.
Yeah, and if the audience really enjoyed this kind of webinar, please follow our page online on the LinkedIn social media. And we'll always have often webinars. You can also access past webinars from our website. So please have a look at it. And yeah, thanks a lot for your attention. And I wish everyone a nice day or evening, depending on where you are in the world. Thanks a lot.
Thank you. Good evening. Bye-bye.
Bye-bye, everybody.
Bye.
Bye.
Visit Sinovoltaics.com to learn more.